basically the diode can be used as a switching purpose. We are basically use the diode. So this diode can be used for rectifier circuit, or can be used for clipper circuit, clamper circuit. So these are the different applications. Now, first, how the diode will be operated. We are already said that the diode basically that the two terminal, anode and cathode terminal. And if we join the p-type and n-type semiconductor material, then a p-n junction is formed. So in previous class we already said that what is p-type semiconductor and what is n-type semiconductor. And you can also familiar with p-type and n-type semiconductor, because in previous semester in physics class you will already get the semiconductor physics, where you can get the idea about p-type and n-type semiconductor. So now, if the p-type and n-type semiconductor are joined, then we get a p-n junction diode. So here we can connect the p-type and n-type semiconductor material. Then a p-n junction is formed, and that is a two-terminal in the p-n junction diode. That is called anode, and this terminal is called cathode. Now, p-type semiconductor material means we have seen that here we can add a trivalent impurity atom. So trivalent impurity atom means it will be create the covalent bond with the parent atom, but it need to be goes to the stable state. Then obviously it needs another electron. So it take another electron from the neighboring silicon atom, then create a hole, create a vacancy. That means p-type semiconductor that can be represented in that way. These are basically consist a free hole, and it will be take the electron. So obviously it can be represented as a negative ion. And if when it will be take an electron, then a vacancy is created. So it can be represented in that way. So it will be take one electron, and it can be behaves as a negative ion. At the same time, when it will be take an electron, a vacancy is created, and that can be represented as a hole. So this type of ion is basically called the acceptor ion, because it accepts one electron from the neighboring parent atom. That means from silicon or from germanium, it can take one electron. So it will be behaves like a negatively charged ion. And when it will be take one electron, then a vacancy is created that can be represented by this hole. So p-type semiconductor that can be represented by a negatively charged ion and free hole. When it will be takes electron, then a vacancy is created that can be represented by hole. So same way, in case of n-type semiconductor, we are basically at pentavalent impurity atom. That means the 5 valence electron in the outermost orbit. Out of this 5 valence electron, the 4 valence electron create the covalent bond, and one electron that is loosely bounded by the nucleus. So for that reason, it can be easily detached, and it can behave like a free electron. So if the electron will be free, it will be behaves like a positively charged donor ion, because it will be donate one electron to the semiconductor material. So for that reason it is called donor ion. So n-type semiconductor that can be represented by a donor ion and the free electron. So this 5th electron in the outermost orbit, that can be detached from the parent atom, then it can be behaves like a positively charged donor ion. And when it is positively charged donor ion, it can be generate a free electron to the semiconductor material. So p-type and n-type semiconductor that can be represented in that way. Now, here we see that the number of holes will be greater than number of free electron. Obviously, some minority charge carriers is also present. These minority charge carriers are free electrons. Say we consider these are the minority charge carriers. In previous class, we have already said that in case of p-type semiconductor material, the majority charge carriers are hole, and that will be greater than a number of free electron. So same thing in case of n-type semiconductor material. Here also some minority charge carriers are present, that is hole, because in n-type semiconductor material, the free electron that will be greater than the number of free holes. So this region, a large number of free electrons are present. This region, the large number of free holes are present. So here the number of concentration of a free electron is much greater than this region. So due to diffusion process, the free electron from the n-type side that can be tried to move towards the p-type side, because we know that in a diffusion process the carrier can be moved from higher concentration region to lower concentration region. So due to the diffusion process, the electron that can be moved from n-type side to p-type side, and at the same time the hole that can be moved from p-type side to n-type side. So this free electron that can be tried to move from n to p, and that free hole that can be moved from p to n. So these are basically called the generation process. So due to generation process, this free electron and free hole that can be diffusion process that can be moved from one region to another region. So free electron and free hole are created if we provide some external energy or due to temperature. This electron and hole will be free, and that electron and hole that can be moved from one side to another side by diffusion process. So if the free electron and free hole is created, that is basically called the generation process. So when the generation process appeared, at the same time, the opposite process will be also function. This opposite process is called recombination. Recombination. That is opposite process of generation. So due to the generation process, we see that the free electron and free holes are created. But the recombination process, the free electron and free holes both are lost. That means when the free electron that can be moved from n-type side to p-type side, and the hole that can be moved from p-type side to n-type side, when the hole reach to the n-type side, here a large number of free electrons are present. So obviously, hole means that is basically the vacancy that is created due to the absence of electron. So here the large number of electrons are present. So obviously this electron can be easily filled up the vacancy. So same thing happened if the electron that can be moved from n-type side to p-type side. Here the large vacancy is present. So electron basically fill up the vacancy. So this process is basically called the recombination process. Or on the basis of energy band diagram, if we discuss this, then we can say that the electron can be moved from valence band to conduction band due to generation process. The electron can be moved from valence band to conduction band through the generation process, and the recombination process, the electron is again jump from the conjunction band to valence band. That is basically called the recombination process. So energy band means that is a band of energy at which the valence electrons are present. That is basically called the valence band. And conjunction band means that is the energy at which the free electrons are exist. That is basically conduct the electricity. This band is called conjunction band. So on the basis of energy band diagram, we can say that the electron can be moved from valence band to conjunction band at the generation process, and the recombination process, it can be moved from conjunction band to valence band. So the generation process, a free electron and free hole is created. Say if we move a electron from valence band to conjunction band, so obviously the valence band, a vacancy is created. So that is basically represented as a hole. And again, this electron will be jumped from conjunction band to valence band. This vacancy is filled up. So obviously, both electron and hole both are destroyed. So recombination process, the free electron and free holes both are destroyed. So here, due to change in concentration gradient, the electron will be moved from N-type site to P-type site. The hole will be moved from P-type site to N-type site. But at the same time, the recombination will be also occur. And due to recombination process, a region is formed near the junction that is basically called PN junction. So near the junction, a region is formed. That region does not contain any free charge carriers. That means does not contain any electron or hole. So this region is basically called the depletion region or phase charge region. So a region is formed after diffusion process, the electron and hole movement occur, and after that a region is formed. That region basically does not consist any free electron or free hole. So this region is called the depletion region or phase charge region. Depletion region or phase charge region. So in this region, no free electron or free holes are present. That region only consists immobile ion. This immobile ion does not carry any current, does not conduct the electricity. These are the immobile ion. So free electron and free hole, that is a mobile carrier. That is basically conduct the electricity. But here in this region, it does not consist any free electron or free hole. That region is basically called the depletion region. Due to the formation of the depletion region, the further electron hole movement is not possible. Because if any electron that can be moved from this side to N-type site to P-type site, it can be repelled by this negatively charged acceptor ion. And if any hole that can be moved from P-type site to N-type site, it can be repelled by positively charged acceptor ion. Sorry, positively charged donor ion. So that means due to this formation of depletion region, further electron hole movement is not possible. That means the total diffusion process will be also stopped. That means the further electron hole movement is not possible. But here we see that in the depletion region, one side consists only positively charged donor ion, and another side only consists negatively charged acceptor ion. So due to the presence of opposite polarity charge carriers, the electric field is created, and the direction of the electric field from this N-type site to p-type site, because their accumulation of positively charged donor ion are present. Here the negatively charged acceptor ion are present, so obviously the electric field that can be directed from n-type site to p-type site. And this electric field is basically called the barrier field. So this barrier field basically that is basically reject the further movement of the free electron and free hole. So that means the further electron hole movement is not possible, and under the thermal equilibrium condition we have seen that no further movement of electron and hole are possible. So if we need to the further movement of electron and hole, then obviously we need some external supply. So if we connect some external supply with the diode, that is basically called the biasing. So using some external supply, we can change the operating condition of the electronic devices. That is basically called the biasing voltage or biasing current. So here we need to apply some biasing signal to the PN junction diode, and by using this biasing supply basically we can change the operating condition of the diode. Now we are connect a external supply in that way. The positive terminal of the battery that is connected with the p-type side, that means anode side, and the negative terminal of the battery that can be connected with the cathode side. So these are a battery DC power supply. So in this DC power supply that can be connected with the PN junction diode. So when this type of DC power supply is connected, that is basically called the biasing. So using this external DC power supply, we can change the operating condition of the diode. That is basically called the biasing condition of the diode. And this biasing is two types possible. One is forward biasing and another one is reverse biasing. So now in that condition, the diode is called forward bias, because positive terminal of the diode, that means anode, is connected with the positive terminal of the battery, and the negative terminal of the diode that is connected with the negative terminal of the supply. So this type of condition is basically called the forward biasing condition. So at that moment, diode is connected in forward bias mode. And due to this forward bias mode connection, we see that here the positive terminal is connected. And due to this positive terminal, this positive terminal of the battery, that is basically repel, the hole will be present in this p-type side, and that can be moved towards the junction. So same thing happened here. The negative terminal of the battery is connected, so this negative terminal is basically repel this electron, and that electron will be also moved towards the junction. So that means electron and hole both move towards the junction. Then the width of the depletion region is reduced. The width of the depletion region, that is the width of the depletion region, that width is reduced. So if we done the forward biasing, then obviously the width of the depletion region that will be reduced. And if the width of the depletion region is reduced, then obviously the carrier can be easily moved again from the p-type side to n-type side and n-type side to p-type side. That means further electron flow occur, and that means the current flow will be also increased through the diode. So if we apply the forward biasing process in the diode, then again the current is flowing through the diode. But if we change the polarity of the supply, if we change the polarity of this DC power supply, That means negative terminal connected with the p-type side of the diode, and positive terminal that is connected with the negative terminal of the diode. That type of connection is basically called the reverse bias connection. And under the reverse bias condition, the negative terminal connected with the p-type side. So it is basically attract the hole, and the positive terminal is connected with the n-type side, that is a cathode side. So it can be attract the electron. So that means the electron and hole that can be moved away from the junction. That means width of the depletion region that will be increases, then the further electron and hole movement is not possible. That means no current is flowing through the diode. So under the reverse bias condition, no current is flowing through the diode, and under the forward bias condition, current flow is possible. So that is basically behave like a same like a switching element, because in switch that have only two states, either on state or off state. So here same thing occur in case of diode. If diode connected in forward bias condition, the current can be flowing through the diode. That means we can say that the device is on. And if the reverse bias condition, no current is flowing through the diode, that means that can say that the diode is off. So for that reason, we can use the diode as a switching element, because it can be also considered the two state, either on state or off state. So if we draw the VI characteristics of diode and the voltage current relationship of diode, then this diagram looks like that. If we just draw the VI voltage current relationship of diode, then we get these are the voltage current relationships. If we apply some external supply voltage, then we can see that the current flowing through the diode under the forward bias condition. And in case of ideal diode, we can consider the diode resistance is 0. Forward resistance of the diode is 0. Forward resistance of diode is 0. Forward resistance of the diode is 0. So forward resistance of the diode 0 means if we connected the diode in forward bias condition, then any amount of current that can be flowing to the diode, and no voltage drop occurs across the diode, because diode forward resistance is 0. So if any current is flowing to the diode, no voltage developed across the diode. So due to forward resistance is 0 in case of ideal diode, for any amount of current can be flowing through the diode, but voltage is equals to 0. Voltage developed across the diode, that is equals to 0. So if we draw the forward characteristics curve of ideal diode, that can be that is overlap in the y-axis, positive y-axis. That is overlap with the positive y-axis. So that means this current axis, positive current axis. Because here the voltage drop across the diode is 0, but any amount of current can be flowing through the diode. And under the reverse bias condition, we know that the reverse resistance of the diode is infinity. Reverse resistance of the diode is infinity. Ideal diode. Reverse resistance of the ideal diode is infinity. Obviously, because in case of reverse bias condition, no current flowing through the diode. So if the current is not flowing through any element, that means its resistance will be very high. And in case of ideal diode, we have to consider this reverse resistance, that is infinity. So current flowing through the diode is 0. But any amount of voltage that can be applied as a supply voltage that can be developed across the diode. So any amount of voltage can be developed across the diode, but no current is flowing through the diode. So obviously the graph that can be coincide or that can be overlap with the negative voltage axis. So that can be overlap with this, because any amount of voltage can be developed across the diode, but the current flow that is equals to 0. So in this position I is 0. Any amount of voltage can be developed across the diode. So these are the characteristics curve under the forward bias condition. That is a characteristics curve under the reverse bias condition. Reverse bias condition. Okay. So these are the VI characteristics curve of ideal diode. VI characteristics curve of ideal diode. Okay. Any question? Any question? We just discussed how to current flow through the diode. And after joining the p-type and n-type semiconductor material, what happened? What is barrier potential? What is depletion region? And what is the process by which the carrier movement occur? That is basically called diffusion process, by which the carrier movement occur. And if we apply some external supply voltage, then the further electron hole movement is occurred. That is basically called the drift. That method is basically called the drift method. So at first the electron and hole movement occurred due to the diffusion process, due to the concentration gradient. But the second thing is due to the application of external supply voltage, the carrier movement occurred. That is basically called the drift movement. Okay. What method means? Roll number 108. Roll number 108. What method? Particular question karo. What method means? Method name is diffusion and drift. Diffusion process means the carrier movement occurred due to the concentration gradient, and drift method means due to the external supply movement, carrier movement occur. That is basically called the drift movement. Okay. So any other question? That is a forward and reverse bias characteristics of a PN junction diode. I think, are you familiar with this part? Basically, I think this part will be discussed in semiconductor physics class. এই পার্টটা জানো তোমরা?
Yes, sir.
Okay, so we just recap of these things. Basically, we start from the application of the diode. In analog electronic circuit, we have just discussed the different application of diode. But we just recap of this thing, that is a depletion region is formed if we get the barrier potential. We need to overcome the barrier potential. For that reason, we need to apply the biasing. Two different type of biasing is possible, forward and reverse. And we can draw the ideal characteristics curve of a diode. Now, we can also see that in case of ideal diode, we can represent it in that way, but practically it is not possible. Practically we seen that the barrier potential that will be present, and we need to overcome this barrier potential. After overcome the barrier potential, the carrier movement is possible. Otherwise, the carrier movement is not occur. So, if we draw the practical characteristics curve of diode, then the characteristics curve looks like that. In this case, we see that after certain amount of voltage, the current will be exponentially increases. The current will be changed in exponentially. So this voltage is basically called the cut-in voltage. Cut-in voltage, and that voltage is required to overcome the barrier potential. After that, we are basically seeing that the current is exponentially increases due to the application of voltage. Due to the application of voltage, the current is exponentially increases. So from this graph, we can easily say that the diode is not a linear element. Say resistor is a linear element, capacitor is a linear element, but in that case, this diode, it is a non-linear element. Here the voltage current relationship is not linear. The voltage current relationship is non-linear. So we can say that it is a non-linear element because here current is exponentially increases. And we write down the equation for this current that can be written in that way. The diode current that is equals to Is into exponential of QV to the power QV by eta kVt minus 1. ID equals to Is into exponential of QV by eta kVt minus 1. So here ID is the current flowing through the diode, Is is the reverse saturation current, Q is the charge of the carrier, V is the applied voltage to the diode, eta is the empirical constant that is basically depend on the material. In case of germanium, its value will be 1. In case of silicon, its value will be 2. Kb is the Boltzmann constant, and T is the absolute temperature. T is the absolute temperature. So ID equals to Is into exponential QV by eta kVt minus 1. And if we just expand this equation, then we can write ID equals to Is into exponential of this part minus Is. And under the forward bias condition, the V is positive. The V positive. So if we apply some positive V, then this term will be much greater than Is. So what is Is? Is is basically called the reverse saturation current. So under the reverse bias condition, we say that no current is flowing, but practically a very small amount of current that can be flowing through the diode, and that current is flowing due to the minority carrier. Because this minority carrier movement can be occur if this minority carrier movement occur due to this barrier field. Because barrier field is directed from the N-type side to P-type side, and due to this barrier field, the hole that is a minority carrier in the N-type side and the electron that is a minority carrier in the P-type side, that can be easily moved from one side to another side. Because the electric field is directed here, it can be provided the force on hole in the same direction. So that means the force on hole in also in this direction. But the force on electron, that is in opposite direction. That means this direction. So electron and hole movement can be easily occur when the diode is in reverse bias condition. So due to this minority carrier movement, a small amount of current is flowing under the reverse bias condition. So when we use a practical diode, we see that a small amount of current is flowing, and that current is very small because the number of minority charge carriers, that will be very small. So for that reason, this current will be very small, and it will be a constant current is flowing through the under the reverse bias condition, like a constant current. So for that reason, it is called reverse saturation current. So this reverse saturation current will be represented by IS. That reverse saturation current that can be represented by IS. So this reverse saturation current of diode is basically in the range of microampere. But the current flowing through the forward bias condition through the diode, that is in the range of milliampere. So obviously the forward bias current is much greater than reverse bias current. So if we expand this equation, ID equals to IS into that part minus IS, so this factor will be much greater than IS. So if we neglect this, then we can easily write ID is nearly equals to IS into exponential of QV by eta KV. So for that reason, here the current under the forward bias condition, that is basically exponentially increases after overcome the barrier potential, and that voltage is basically called the cut-in voltage. So same thing in case of reverse bias condition, the voltage is negative. So here if we provided the negative V, e to the power minus something, that means that term will be very low with respect to 1. So if we neglect this, then we get ID that is nearly equals to minus IS. So for that reason, you can see that under the reverse bias condition, the current flowing through the diode, that is a constant current and very small current, that is basically called the reverse saturation current. So these are called a practical diode. Practical characteristics curve of diode. PI characteristics curve of practical diode. Now, if we use the diode in different circuit, then we are already know that in circuit theory we are already get that if we apply the Thevenin's theorem or Norton's theorem or superposition theorem, all this electrical theorem that can be basically applied for linear component. That means if the circuit consists linear component, but diode is a non-linear component. So in any circuit, if we need to calculate this type of different electrical law, say KCL, KVL or Thevenin's, Norton's or superposition theorem, if we need to apply, then obviously in that case the element must be linear. So for that reason, we are basically take some approximation, or we can done the linearization of this element, linearization of this diode element. So if we done the linearization, then we can use this type of curve. We can consider say that is basically some approximation. We consider after cut-in voltage, current is sharply increases like ideal diode. We are take this approximation first. So if we consider this, then obviously the cut-in voltage that can be also represented as V like this. So if we consider this type of approximation, the approximation is that the diode is used as an ideal diode. After cut-in voltage, the current is sharply increases like a ideal diode. So in that case, the diode can be represented in that way. Say a diode is present, that can be easily represented by this way. If it will be overcome the cut-in voltage, if it overcome the cut-in voltage, then it can be behaves like a closed switch under the forward bias condition. Under the forward bias condition. So this approximation is basically called, if we consider here the current is sharply increases like an ideal diode, up after cut-in voltage overcome the cut-in voltage. After overcome the cut-in voltage, the current is suddenly increases like ideal diode. So in that case, we can easily represent the diode in that way. It just overcome the cut-in voltage, and after that it can be behaves like a closed switch. So if we take this type of approximation, then that can be represented by this way. So in case of ideal diode, the diode can be represented in that way. That is a forward bias condition. Under the forward bias condition, it can be represented as a closed switch. These are the positive terminal of the diode and negative terminal of the diode, and it can be represented as a closed switch under the forward bias condition. But if we represent the practical diode, but we take some approximation, and we can consider this type of approximation, then the diode can be represented by this way. It can be overcome the cut-in voltage, and after that it can behave like a closed switch. So when we take this type of approximation, will be taken. Now we can also take another approximation that is basically called the piecewise linear approximation. So piecewise linear approximation is that here these are a non-linear portion. That section is the non-linear. So if we consider a small region of this section, say a very large region and a non-linear region is present like this. If we consider a small region, then it can be represented as a linear region. Say we take only this region, only this small region, then it can be represented as a linear region. Or we can take only this section, then we can say this region is linear. So we can take the approximation of this nonlinear element by this way. We are taking a small region and we can consider that region is linear, and by taking the difference in voltage and the difference in current, we can easily calculate the incremental resistance of this region. So basically, diode is a nonlinear element and resistor is basically the linear element. So in case of nonlinear element, the resistor is not present, but we can consider a small region of these characteristics are, and that region will be considered as a linear, and from this small region we can calculate the change in voltage and change in current, and from where we can calculate the incremental resistance of the diode. And we can consider, say, this approximation is that if we consider that region as a resistive region, then obviously the current is linearly increases like this. So this type of approximation is called piecewise linear approximation, because in this region the current is 0. After that, this region the current is linearly changes. So we can consider these are the piecewise. That section is current 0. This section current is changes like a resistor. So we apply the voltage in a resistor, the current is linearly changes. Same thing happens here. We are taking the approximation on the basis of this. That is basically called the piecewise linear approximation. So now, if you take the piecewise linear approximation, then obviously in that case the diode can be represented by, diode can be represented by a cut-in voltage. After that, it can be behaves like a resistor. After that, it can be behaves like a resistor, and this resistor is basically called the AC resistance of the diode. AC resistance or dynamic resistance of the diode, because here can calculate the change in voltage by change in current. We are calculate the resistance value, and this resistance value that can be changes with the operating point. Say here we take the operating point in this region. Now if we change the operating point here, the resistance value will be also changes. So resistance value depend on operating point. For that reason, it is called dynamic resistance. So if we consider a resistor, its value cannot be changes for any region, any operating point. If you calculate the ratio of voltage by ratio of voltage and current, always get the same value. Its value cannot be changes. That means if we change the operating point, the resistance value cannot be changed in case of resistor. But in case of diode, if we change the operating point, say if we consider, if we calculate in this point, that is the operating point, the resistance value, we get some resistance value. If we change the operating point from here to here, its value will be changes. If we change the operating point from this point to this point, its value will be again changes. So the resistor value, that will be totally depend on the operating point. For that reason, it is called dynamic resistance. So dynamic resistance or AC resistance that can be connected in series with the cutting voltage. So diode can be represented by this way if we consider the piecewise linear approximation. So now nothing. Diode is an electronic component, but here we can draw the two circuit by taking the approximation.